This Explain Everything video is intended as an instructional resource to help teachers more effectively conduct the lesson as described in the teacher notes in this unit. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. The more ways that an outcome can occur, the more likely it is for that outcome to occur. Why is it more likely to get 6 heads than 8 heads when you toss 10 pennies? We can use the combination formula to determine the number of ways that you can get 8 heads when you toss 10 pennies. This is given by 10 factorial divided by 8 factorial times 2 factorial. This works out to be 45 ways. Use of the combination formula shows that there are 210 ways to get 6 heads when you toss 10 pennies. There are 2 to the 10th or 1024 possible outcomes. So you can see that the odds of getting 6 heads are nearly 5 times as great as that of getting 8 heads when you toss 10 pennies. These values apply to the odds of getting 2 heads or 4 heads because these events are the same as having 8 tails or 6 tails respectively. In the Boltzmann game article, the authors show how you can calculate the number of ways that out of 24 students, 10 could have no money, 8 could have $1, 4 could have $2, 1 could have $3, and 1 could have $5. Let's briefly review the math. 24 choose 10 gives the number of ways 10 students could have $0. 14 choose 8 gives the number of ways 8 of the remaining 14 students could have $1 each. These account for 18 of the students. 6 choose 4 gives the number of ways 4 of the remaining 6 students could have $2. 2 choose 1 gives the ways 1 of these remaining 2 students could have $3. Finally, there's only one way the last student could have $5. The authors show that this number comes to nearly 177 billion. You are invited to calculate the number of ways each of these 3 distributions could occur. Here are the number of ways obtained in each of the 3 rounds. The numbers can vary, and sometimes it even happens that a later round will produce fewer ways than an earlier round, but that's due to the fact that their sample size is so small. Generally speaking, as the distribution spreads out, the total number of microstates corresponding to that macrostate increases. The authors define entropy S as Boltzmann's constant K times the natural log of the number of microstates associated with the given distribution. A more useful measure is delta S, which compares the number of microstates in the initial and final conditions. Since entropy is a logarithmic function, delta S is a measure of the relative probability of the final distribution to the initial distribution. But we're going to use a more conceptual approach to this treatment. The change in entropy is positive when the number of ways an event can occur increases. The change in entropy is negative when this number of ways decreases. The change in entropy is 0 when there is no change in the number of ways something can happen. And for a system with multiple components, the total change in entropy is equal to the sum of the changes in entropy of each of the components. For an event or process to be thermodynamically favorable, now preferred to spontaneous, the number of ways that the final state can exist must be greater than that in the initial state. So when the change in entropy is positive, the process as written is thermodynamically favorable. When the change in entropy is negative, the process is so unlikely that the reverse process is thermodynamically favorable. And when the change in entropy is zero, the system is at equilibrium. Let's consider the entropy change for the thermal process that occurs when a hot object is placed in contact with a cold one. A quantity of thermal energy leaves the hot object and enters the other. We assign a negative sign to the amount of energy that leaves the hot object and a positive sign to the amount of energy that enters the cold object. We define delta S thermal as a measure of the number of the ways energy can be distributed amongst the particles in the object. It seems reasonable that delta S thermal for the hot object will be negative. As energy leaves the object, there will be fewer ways for the remaining thermal energy to be distributed. Delta S thermal for the cold object will be positive, since there will be more ways for energy to be distributed amongst the particles. Therefore, delta S thermal has the same sign as Q. From conservation of energy, we know that the magnitude of the energy lost by the hot object equals the magnitude of the energy gained by the cold object. We also know from experience that this process is spontaneous, so delta S thermal total must be greater than zero. Evidently, delta S thermal depends on some other factor than Q. This factor is the Kelvin temperature. We define delta S thermal as Q over T. Take a moment to reflect why this definition of delta S thermal explains that this process is thermodynamically favorable. You might try substituting values in for Q and T to help you with your reasoning. You should also be able to explain in terms of Q and T why it is improbable for thermal energy to spontaneously leave the colder object and enter the hot one. We have seen that when the temperature of the surroundings is greater than that of the system, it is more probable for energy to flow from the surroundings to the system than the other way around. However, the system can store energy in more than just the thermal account, as we have learned earlier in the course. Phase energy and chemical energy accounts are also available. How does the energy entering the system end up in the right account? Consider our system to be an isolated ice cube. If no energy change were involved with melting, it would be structurally more favorable for water to exist in the liquid state than in the solid state. This is due to the fact that there are many more ways to randomly arrange molecules in the liquid state than in the solid. However, melting requires a transfer of energy, 6 kilojoules per mole, from the thermal account to facilitate the structural change. Such an energy transfer reduces the number of ways the remaining thermal energy can be distributed among the molecules of H2O. We define the quantity S structural as a measure of the number of ways in which the particles of a substance can be arranged in space. A positive value for the change in structural entropy indicates an increase in the number of ways the particles can be arranged. A negative value indicates a decrease in the number of possible arrangements. This value is mostly independent of the temperature. So when solid water changes to liquid water, the value of delta S structural is positive and the value of delta S thermal is negative. That's because the system is transferring thermal energy into the phase energy account. The total entropy change for the process of melting is the sum of the changes in structural and thermal entropy. From our definition for delta S thermal, explain why it's unlikely for ice to melt at minus 5 degrees Celsius. On the other hand, ice is likely to melt at positive 5 degrees Celsius. Hopefully you concluded that because delta S thermal is inversely proportional to the temperature, as the temperature increases, the magnitude of this term decreases. At 273 Kelvin, delta S structural and delta S thermal have about the same magnitude. At higher temperatures, delta S structural wins out. We've seen how raising the temperature makes delta S total greater than 0, so that ice is likely to melt. Now let's consider a way to make delta S total greater than 0 without adding thermal energy to the system. When sodium chloride is added to an ice-water mixture, the presence of the sodium and chloride ions increases the number of ways the molecules of liquid water can arrange themselves. This increases the magnitude of delta S structural so that this factor dominates. First, we might need to convince the skeptic that adding sodium chloride to water doesn't increase its temperature, thereby melting the ice. Here we have 15 grams of sodium chloride that we're adding to about 200 milliliters of water. The graph of temperature versus time shows that the temperature is virtually unchanged by the addition of the sodium chloride. Here we are prepared to add the same mass of sodium chloride to the same volume of the ice-water mixture. The ice melts even though we did not supply energy to bring about this change. Eventually, the surroundings will transfer energy to the system, but that is a consequence, not a cause of this change. The final question we must consider from an entropy standpoint is, why did the temperature level off?